focus of this tutorial is to take some of the ideas we learned in the concentration tutorial on the different types of concentration expressions and use those ideas to solve problems. So we're going to take a look at 4 different problems, each involving different concentration expressions. So in looking at the first problem here, I'm going to highlight some of the key information for you. So we've got the household bleach that has a concentration of 4.60% mass volume, and the mass of, and we want to find out the mass of sodium hypochlorite, so the mass of the solute, and we have 2.84 liters of the bleach. And so what we want to do here, it looks like in the given information section, I've said that we know the concentration of the bleach, we know the volume of the bleach or the volume of the solution, and what we're trying to find out is the mass of the NaOCl, the sodium hypochlorite, which is our solute in this case. As I mentioned earlier, there's a formula in your textbook that you can use, but I prefer to use the idea that we talked about in the previous tutorial, where we have a mass volume percent concentration actually means the grams of solute that you have per 100 milliliters of solution or per 100 milliliters of bleach. And so in this case, we have the 4.60% mass volume is equivalent to 4.60 grams for every 100 mils of bleach. Now to solve that, we can take the concentration value that we've converted to grams per 100 mils, and we can multiply that by the volume of the solution, which was originally expressed as the 2.84 liters, but we converted it to milliliters to have a common set of units that will cancel out. And multiplying that, we get this value here. Note that the answer is expressed to 3 significant figures because both of the given pieces of information have 3 significant figures. And so we have our statement that summarizes the work that was done, and then a check here, and the check is to say that the mass of our solute should be greater than 4.60 grams, and it is. It's 131 grams, because the volume of bleach that we have is greater than 100 milliliters. What I mean by that is, since we know that in every 100 milliliters there's 4.60 grams of the NaOCl, we should have more than that because we have more than 100 mils, i.e. we have 2,840 milliliters of the bleach. Taking a look at problem number 2, we've got a similar type problem here. The key pieces of information, we've got this concentration expression, 75% mass, and that's the concentration of gold in the jewelry. And we are asked for how much of the alloy can a jeweler make with 8 grams of pure gold. And so this time we're given the concentration, right, in 3 significant figures, and we are told what the mass of the solute is. That 8 grams represents the mass of the solute. And what we're looking for is, what's the mass of the 18 karat gold? So what's the mass of the solution, or this alloy? And so again, I'm going to take this percent expression and I'm going to convert it to units that we can work with. So I'm going to say that 75% mass actually tells me that we have 75 grams of gold in every 100 grams of our alloy. So now I want to arrange my numbers so that my units cancel out and I'm left with the units that I'm trying to find. I'm trying to find grams, and I'm trying to find specifically the grams of the alloy or the solution that are needed. And so I want to arrange my values here so that the grams of gold right here and the grams of gold right here are arranged in numerator and denominator and cancel out. And then I take care of my numbers by multiplying the 8 by 100 and dividing by 75, which gives me the 10.7 grams. And that value is listed to 3 significant figures. And my check there is to say that, you know what, the mass of the alloy solution, which is 10.7 grams, is greater than the mass of the solute, because obviously there is a greater amount of the overall solution than there is of the solute, the 8 grams of gold that was in the 18 karat gold alloy. So taking a look at question number 3 now. Now we move away from the percent concentration expressions and move into some of the part per million expressions. And remember that these part per million expressions are used for really low concentrations. And so here we are told that we have a 600 ppm solution of lead, and we're trying to find out the maximum mass of lead in 7 kilograms of paint. And so the 600 ppm is our concentration. The mass of paint that is given is actually the mass of the solution, and the mass of lead that we are trying to find is the mass of our solute. And a couple of things to note here. So the 600 ppm only has one significant figure, and that's going to influence the number of significant figures that I can have in my answer. As I mentioned, the paint is the solution, and we have the units of kilograms, which will actually turn out just fine. And we'll end up with an answer in milligrams. And remember I said that, and we'll go down here to the analysis part, if we have 600 ppms, a way to convert that from ppms into a more functional set of units is to say that that is equivalent to 600 milligrams per kilogram. So essentially the concentration of this paint is, or it can't contain more than 600 milligrams per kilogram. And so if I include that piece of information down here and arrange my units so that the kilograms will cancel out, because we know we want to be left with a final answer of milligrams. And specifically, if I want this is my kilograms of my solution, and this is referring to the kilograms of the solution, and so those should cancel out. I multiply, or I carry out the operations. I'm left with the 4,200 milligrams, which represents the mass of my solute, but I have to write that to an appropriate number of significant figures, which is either right here with 4,000 milligrams, only containing one significant figure, or 4 grams. And so I write my final statement, and then my check would be that the paint has a mass of 7 kilograms, therefore the mass of the solute should be greater than 600 milligrams. And again, because we know that in every 1 kilogram of paint, you are allowed to have 600 milligrams of lead. So since we have 7 kilograms of paint, there should be greater than 600 milligrams of lead, and that's what we indeed find up here. So in this final problem, we are going to take a percent concentration value and determine the molar concentration of this value. And the only two real pieces of information that were explicitly given, or the only one, is the percent concentration value right here, which I recorded. But we are also told that the formula for formaldehyde is the HCHO. From that, we can determine the molar mass of the formaldehyde. And we know that we are being asked to determine the final concentration in moles per liter, which means that I need to somehow incorporate moles and liters into my final answer. So let's see what happens when we kind of unpack this concentration value, take a look at its units, and how we can use those units to help us find the answer. So first thing, the 37% mass volume, we can convert that to units involving both grams and liters, or grams and milliliters, as I say, because remember that we have the 37% mass volume is equivalent to saying that we have 37 grams of the solute in every 100 milliliters of solution. But we know that we want to get an answer in moles per liter, and so it would probably be more beneficial if we take this piece of information right here and convert it to liters. So 37 grams for every 0.10 liters, keeping in mind that 0.100 liters is equivalent to 100 milliliters. So these two statements, or these two factors, conversion factors, are equivalent. I've just wrote in grams kind of per 0.1 liters instead of grams per 100 milliliters. So now if I figure out the number of moles that 37 grams is equivalent to, then I will have the number of moles in 0.1 liters, which will eventually allow me to calculate the moles per liter. And so that's what number 2 I say to determine the number of moles in 0.1 liters, and we do that using that molar mass value from up above, and this should be a calculation that is familiar to you from the previous unit. We calculate the number of moles, keeping in mind that we do only have 3 significant figures, but it's a good habit to write down more digits and then round in the end. I figure out or determine the concentration by dividing the number of moles by the number of liters, and we get 12.3 moles per liter. One thing that I forgot to highlight up above, note that for the concentration expressions, that we use a capital C for basically the non-mole per liter concentration expressions, so a capital C there for those percent concentrations, and I believe for ppm and ppb as well, whereas we use the lowercase c when talking about concentrations in moles per liter. And so finally, my check is we've got more than 1 mole's worth of formaldehyde in 100 milliliters, as calculated right here. Therefore, our concentration should be greater than 1 mole per liter, because remember, 1 mole per liter, the capital M also represents mole per liter, is telling you the number of moles in every liter, and we've got 1.2321 moles in 100 milliliters, so we should have 10 times that amount in 1 liter, which is what we see here. So overall, what we've done here is learn some different strategies for solving concentration problems dealing with different expressions. And so now would be a good time after watching this to go and practice some on your own and see if you can apply some of these strategies on your own.